Flipped classroom video for Maths A2 Unit 3, Inverse and Composite Functions. Okay, inverse functions, one-to-one only. We've come across a number of inverse rules. For example, we have x squared and root x. Now, we've already seen that for the square root, we generally, when we're talking about functions, we restrict to the positive root. But to make the functions inverses of each other, we would need to define the domain, if we're looking at x squared, so that the function is one-to-one. And the reason for this is, if we take an x value and say what happens if we put that into the x squared function, that's fine. If we put 1 into x squared, we get 1. But if we try and go backwards and say we got the answer 1 after doing x squared, where did it come from? Well, that could have come from 1 or from minus 1. And that means the inverse or undoing x squared would not be well defined. So what we can do is we can restrict the domain of x squared to being x is greater than or equal to 0 or between 0 and infinity. And then we can see that that is one-to-one, and so root x is indeed the inverse of x squared with that domain. We could have done it the other way, in which case we'd have had the portion of the square root that's below 0, but we would call that the function minus root x. So sine x and sine to the minus 1 of x. We can see that the sine curve is multivalued. In fact, we know it carries on forever, so it's multi-valued. All y values come from lots of x values. So we have to restrict it. The detail for this is in a video M2.3.5b3, which is called Inverse Trigonometric Functions, I believe. But anyway, what we do is we restrict the domain to be from minus pi by 2 to pi by 2, and so we can again see that that makes it so it's one-to-one. E to the x and log x, well, this is actually included to show that sometimes the inverse rules play nicely. In this case, e to the x is already one-to-one, and therefore we can just have the full domain from minus infinity to infinity. The range, of course, is just from 0 to infinity for this particular function. Now, functions and their inverses are reflections of each other in the line y equals x, always. And this can be very useful if we want to sketch inverse functions. We'll put the reflection lines in so you can see it. And it's not a surprise that they should be reflections of each other, and it's worth a bit of thought. So we'll look at the relationship between a function and its inverse, which is of course also a function. If we have a one-to-one function f mapping the domain of f to the range of f, which of course it always does, we can represent that by two sets, so the red and the green, and we label them domain of f, range of f, and we show that f maps from a value p or an element p onto f of p in the range. We can also give an example of that in a sort of graphical way. So we have this function. Because we're dealing with inverses, you can see that the purple representation of the function is indeed one-to-one. We can see that the domain are the x values that are being mapped. We can see that the range is the y values that come out of the mapping, and we can see that the value p, when we go up to the graph, gives us the value f of p. So that's another representation of the function. Now, if we have a one-to-one function, then it will have an inverse function. And the inverse function will map from the range of f, which becomes or is the same as the domain of f to the minus 1, and it will map onto the range of f to the minus 1, which is identical to the domain of f. And we show the mapping by putting f to the minus 1 and the arrow going from q to f to the minus 1 of q. And we can show this again on the same graph. Actually, it's identical. It's just that we've now, instead of saying the range of f, we said the domain of f to the minus 1, and instead of the domain of f, we've got the range of f to the minus 1, and we're showing a value q in the domain of f to the minus 1 going to its image in the range of f to the minus 1. So it's taking things backwards, basically. So f to the minus 1 acts on the domain of f to the minus 1 and going to the range of f to the minus 1. So clearly, as I mentioned already, the domain of f to the minus 1 is identical to the range of f, and the range of f to the minus 1 is identical to the domain of f. We can also say that if we take a value y equals f of x, then we can say that x must be f to the minus 1 of y, because it's the opposite or the inverse function. And if we substitute that x is f to the minus 1 of y into the line above, we have y equals f of f to the minus 1 of y. Similarly, we could do it the other way around. We could say that x is f to the minus 1 of f of x. So it's telling us that f and f to the minus 1 essentially cancel out, which is the same as what happens with numbers. 3 times 3 to the minus 1 is 1. F followed by f to the minus 1 is equivalent to 1 in that it doesn't do anything functionally. Okay, now we're going to have a look at composite functions. A function of a function. So a composite function is one that is made up of a combination of functions, which is sort of obvious, I guess. So let's have a look at a couple of functions. We've got f of x is 2x minus 1 and g of x is x squared. And we're not going to worry about domains and ranges just for the moment. G f of x means g applied to f of x. Although we write it without the extra set of brackets, it's important to realise that's what we're doing. We're applying g to the result of applying f to x. And that means we can write g of, in this case, 2x minus 1. And then, because g of x means squaring whatever x is, we have to square 2x minus 1. And that gives us 4x squared minus 4x plus 1. On the other hand, if we go the other way round, fg of x means f applied to g of x. So that means f applied 2x squared. And that means we're going to take 2 of whatever's in there and take 1 away, which means we have 2x squared minus 1. So we can see that two functions put together as composite functions the opposite ways round are very definitely not always the same. Sometimes they are, but generally not. What about domains and ranges in this situation? Well, as the domains are not specified, what we generally do, we assume that they are the largest domain that they could be, and in this situation there's no reason for eliminating any values. There aren't any values that are impossible for these functions, so we assume that the domain for each of them is from minus infinity to plus infinity, or the set of the real numbers. A little working out or thought tells us that the range of f is the real numbers and the range of g is from 0 to infinity, so the positive real numbers. And when I say a little working out or thought tells us that, let's do that. F, the function f, is a straight line, and it has a gradient that's not 0, so it goes from minus infinity to plus infinity in both ways. So the range will indeed cover all the numbers. G of x is x squared, and we know that the function x squared makes all the negative numbers positive. The positive numbers stay positive, so we will only get positive numbers. So it's fair enough for us to conclude that the range will be indeed 0 to infinity. Now, let's represent the domain of g and the range of g in this way. So we have these two sets. G maps the domain of g onto the range of g. So this is the function x squared. And what we know is that the range of g is from 0 to infinity. The domain of f is actually from minus infinity to plus infinity. So that means the range of G is included in the domain of F. We then can map the domain of F onto the range of F, which is shown by the arrow and F. But we can also map across only the portion that was the image from G, so G of the domain of G. When we apply F to that, we get Fg applied to the domain of G, which is the blue subset inside the range of F, so that is now the range of Fg. So the range of Fg lies inside the range of F, and everything's fine. So the key point here is that the range of G is from 0 to infinity. That is included in the set from minus infinity to plus infinity, which is the domain of F. Point being, the range of G is inside the domain of F, and so we are able to make the composite function. Because when we apply F, having first applied G, all the elements or numbers involved are in the domain of F, and we can therefore apply F. Oops. What if the range of G does not lie in the domain of F? We'll again show this diagrammatically. We have the domain of G and the range of G. We have the function of G mapping from the domain to the range, and therefore the blue set is G applied to the domain of G. That gives us the range. Now we'll introduce the domain of F, and as it says at the top, the range of G is not included. That's what that symbol means, not part of, not included in the domain of F. So there are parts of G which are outside. So those bits at the bottom there, we can see there are elements that are in the range of G that are not in the domain of F, and that arrow, the black arrow, is coming from that portion, and we want to try to apply F to it, but we can't because F only applies to the domain of F, and because that value is not in the domain of F, we're not allowed to apply F to it, and that means we cannot form the function fg of x. Let's take an example. If f of x is 2x minus 1 and h of x is the square root of x, the domain of f is from minus infinity to infinity, and the domain of h is from 0 to infinity. Does h f of x exist? And the answer is no, because the range of f is not included in the domain of h. And we can just consider a value here if we want. If we consider f of minus 4, that's 2 times minus 4, take away 1, which gives us minus 9. And minus 9 is not a member of the set from 0 to infinity, which is the domain of h, so we can't apply the function h to this value. What we can do is to restrict the domain of f so that its range lies within the domain of h. And we can do this by doing a quick sketch of the situation. We don't need a sketch necessarily, but as you'll know from watching some of these videos, we like our sketches. So those are the points on the x and y axis where f of x as a line would have to travel through. We want the domain to be from 0.5 to infinity, because that will make the range of f 0 to infinity. So basically we're looking at that green line, we're seeing where it's above 0, which is what we need to match the domain of h, because that starts from 0 and goes up. Well, it doesn't include 0, but it goes up from 0. And so we're going to let our domain be from 0.5, not including the value 0.5, up to infinity. We can then form h f of x, which is h of f of x. That's h of 2x minus 1, so that's the square root of 2x minus 1. And the domain is from 0.5 up to infinity. Now this is often a topic students find difficult because it's quite sort of abstract, and it's like there's a lot happening but not a lot happening. It's an odd sort of topic. But one thing to bear in mind here is that if you've ever come across, and you may well have done at some point, the function square root of 2x minus 1, then you wouldn't have been too troubled by what numbers you could use in it. You'd try numbers in it, and if they happen to be negative numbers, once you'd done the 2x minus 1 bit, you'd just said, oh, well, you can't do that, and just forgot about it. What we're doing here is formalizing those sort of ideas, which is necessary for developing the theory of functions further.